Hello, this is the third video lecture in our fluids unit, and the topic is the buoyant force. The essential question for this video is, why do some things float? And I hope when you hear that essential question, you're thinking, I already know the answer to this because you probably learned it in middle school. And the answer is, of course, objects float if they are less dense than the fluid that they sit in. Hopefully most of you are familiar with that. But I guess my question is, but why do they float? Not just because they're less dense. I want to know at a really deep physical level why being less dense has any effect on an object floating. So that's what we're going to get to in this video. So one of your assignments outside of class was to do a little practice calculation, which you may have just thought was me forcing you to do a whole lot of extra hydrostatic pressure work. But it turns out that that problem about calculating the pressure on all sides of a cube wasn't just busy work. That's actually the foundation of the buoyant force equation that we're going to get to in a minute. We know, just to revisit, the hydrostatic pressure exists on any object under a fluid, and that it pushes in on all sides of the fluid, not just down on the top. We also know that this force increases with depth. So here's kind of a schematic representation of an object that's underwater experiencing hydrostatic force on all four sides that you can see in the picture. The cool, interesting thing about this hydrostatic force is the sideways force is going to cancel out, right? You can see every force to the right is balanced out by an equal and opposite force to the left. However, when you look at the up and down forces, they don't cancel out because the top of that object is not as deep as the bottom, and therefore the upward force on the bottom is actually greater than the downward force on the top. When you simplified this net force due to fluids on the object and canceled out all the stuff and then subtracted the top from the bottom, you end up with an equation that can be further simplified to rho GV, which is an equation that we're going to be dealing with a lot in the rest of this unit. Okay, on this slide, we're going to be going through the details on this force called the buoyant force, which is represented by a capital F and a lowercase b. You already derived the equation on the last slide in that other activity, but we're going to be talking about the details of that equation in more depth. So the buoyant force is defined as the upward force on an object surrounded by any fluid, and that's any object in any fluid. So you're an object and you're surrounded by the fluid of air, which means you actually have a buoyant force acting on you right now that's trying to hold you up, which is kind of cool that you may not have realized. The buoyant force, according to that equation, is linear with the density of the fluid. And the reason why is because when you go underneath a dense fluid, the pressure increases at a higher rate. It goes up faster under a dense fluid. So we have a bigger difference between the pressure on the top and the bottom when the fluid is dense. A note about this, and I underlined it and made it bold too, be careful not to use the density of the object if you are trying to use this equation. If you put in the density of the object, you're going to get a totally different answer. So it's always the density of the fluid that matters because that's what's creating the hydrostatic pressure, not the object. The second variable in this equation is the volume of the submerged object. And the reason why is because a bigger object with more volume is going to also have a bigger difference in pressure because there's going to be more space between the top of that object and the bottom just based on its size. Again, an important note about this, we're only talking about the submerged, the amount of the object under the fluid, not the entire volume of the object. So if you have an object that's floating partially out of the water, the only part of the object that's generating buoyant force from the water is the part that's underwater. So you only want to use the chunk of the fluid or chunk of the object that is under the fluid. The third thing is the planet's gravitational field strength. And again, we kind of talked about this before, but the pressure differential is bigger on planets with a stronger gravitational field. So this is why it matters in this equation as well. Boils down to this equation, which you should find on your AP equation sheet, which is FB equals rho GV. So we need to understand this force because we will be using it on free body diagrams regularly. This is the unit in this class when we do probably the most and the most complicated free body diagrams. So it's really important that you guys have watched that video on forces and free body diagrams and reviewed those skills if they weren't something that you spent a lot of time on in a previous physics class. Reminder, every object, so any object in a fluid has a buoyant force, and that should now appear on its free body diagram. You can calculate that force directly if you know some properties of the fluid or properties of the object. Other forces that you may include in free body diagrams that are involved with the buoyant force are gravity. Of course, if the object's on Earth, you should put gravity on there, and there's an equation to calculate that directly, right? The mass of the object times the gravitational force field of the planet, so you can calculate that one directly. Second force that commonly appears is the normal force, but a reminder that that only is going to go in your free body diagram if there's a solid surface pushing on the object. So an object that is sunk into the bottom of the ocean would have a normal force holding it up, but an object that's floating on the surface of the ocean doesn't have a normal force because nothing's pushing on it. Unless, for example, a bird landed on a raft or something, then you'd have the normal force downward from the bird because that's solid. But unless it's touching something solid, we don't put normal force in our free body diagram. The third force that sometimes comes up is tension. This is often balloons or blimps, those kinds of objects that have strings or cables attached. And tension always acts in the direction of the string. A couple reminders from Newton's laws videos. If the object is not accelerating, so if it's just hanging out floating or hanging out sunk at the bottom of the ocean, all the forces are going to be balanced. So this is primarily represented in floating objects and sunk objects. Sometimes we encounter an object that is accelerating. So this would be an object that is maybe falling through the ocean and accelerating, or like a balloon, when you let go of a balloon, it would accelerate upwards. And in those cases, the forces on the free body diagrams are going to be unbalanced, and we could calculate the acceleration of the objects based on Newton's second law. So this is F equals ma, or A equals sigma F over m. Find the sum of the forces and use that in this equation. All right, that was kind of a lot, those last two slides. I hope you paused them and revisited them and really own the stuff that's in them, because it's all pretty critical stuff. But I thought I would just do a quick little stretch break. So stand up, check out this adorable manatee. I found this fun fact on the internet that manatees can control the buoyancy of their bodies through an endless cycle of farting. And hopefully now you can think back to that buoyant force equation and think about, why would farting control a manatee's buoyancy? So pause the video for a second, think about it, and come back. So hopefully you realize that when you fart, what's happening is two things. You're sending out a bubble of gas, which has properties of mass, and it also has properties of volume. It's going to have a very little mass and a lot of volume, relatively speaking, because gases are not very dense. So in any case, what's happening to the manatee is that the manatee's volume is decreasing because it let go the volume of the gas, and its mass is only going down by a little bit, which means that the buoyant force acting on it, rho GV, is going to go down when it farts because it's decreasing the volume of the manatee. Kind of crazy. Okay, I'd like to run through a few sample free body diagrams. For each one of these, I'd recommend that when I present the scenario, you actually pause it and draw it yourself, and then restart the video and see if your drawing matches mine. So the first is a block of wood floating in water. This could also be a boat or a raft, anything that's floating in water. So pause, draw it. Okay, so this is how I created my free body diagram. I started with my object. The first force I almost always put in is the force of gravity from Earth, assuming that we are on Earth. And then the second force I would put in would be a buoyant force from the water holding it up. A little note about this, there actually would be another buoyant force from the air. That is, if this object's floating, part of the object is going to be in air. But I'm not actually going to put that in my free body diagram because it's going to be really, really negligible. In general, air buoyancy we only include when we're talking about balloons and blimps and those kinds of things, because otherwise it's such a tiny value it doesn't make any difference. A few notes about this free body diagram. Since the block is at rest, floating in the water, that means that these forces have to be balanced, right? FB minus FG equals 0. That's one way to write mathematically that these forces are balanced. Or it boils down to FB equals FG, right? They have to be equal in size. So you could have drawn those little symbols on to represent the fact that those forces are actually the same up and down. And that can help you calculate lots of things about the object. If you know one of the forces, it helps you get into solving some of the properties of the fluid or properties of the object that you might be interested in. Second free body diagram, a block of metal at the bottom of a lake. So pause. Okay, starts the same way. We've got our object, and I'm going to put gravity on that block of metal as well. I drew that force a little bit longer than the block of wood, although I actually don't know that it is. We didn't get the masses of these objects, but just for fun, I drew it bigger. And I'm going to put buoyant force on that block of metal as well. You will notice, because it's underwater, you'll notice I did draw that buoyant force smaller than the force of gravity, because the buoyant force isn't enough to hold up the block of metal, right? Block of metal put in water is going to sink. So the buoyant force is not going to be as big as gravity. However, this block of metal is already at the bottom of the lake, which means we have another force acting on it as well. We have the normal force from the ground at the bottom of the lake pushing upwards on the block of metal. Now, just like the last scenario, these forces actually have to be balanced as well, because this object is at rest, sitting at the bottom of the lake. If I wanted to write a mathematical equation to represent the forces acting on the block of metal, I would write something like this. FB plus Fn, right, my upward forces, minus my downward force, which is Fg, have to be equal to 0 because we are at rest and we're not accelerating. Okay, I've got two more free body diagrams I want to go through. The first is a helium balloon that is being held up by a string. So pause the video and see if you can draw that free body diagram and write an equation if you can. So there's my helium balloon. Looks a lot like my block of wood from the last slide. I'm going to start by putting the force of gravity on the helium balloon. Even though it is small and doesn't have a lot of mass, it does have some mass, and Earth is pulling downward on that mass as well. I know there's a buoyant force acting on that balloon, trying to hold it up. In this case, the fluid surrounding it is air. So this is one of those cases where you would want to use the buoyant force from the air because it's not negligible for the balloon. It's significant in the case of the balloon. And there's one more force acting on that balloon, and that is the string that you're holding onto has the force of tension pulling downwards on that balloon. Since the balloon is at rest, we know these forces have to be balanced, just like the balanced free body diagrams from the last slide. And you could write an equation, hopefully you did. Upward forces FB, so that's positive, minus FT, minus FG, have to be equal to 0 for all balanced non-accelerating objects. Second free body diagram. What happens for the same balloon when the person let go of the string? So go ahead and pause the video, see if you can draw the free body diagram and write your equation. Free body diagram should be pretty straightforward. I'm going to put gravity because letting go of the string doesn't change the gravity acting on it. Letting go of the string doesn't change the buoyant force. Nothing in that buoyant force equation has to do with the string. The only thing it affected was the tension, right? When I let go of the string, no more tension. So that guy went away. So now this is my new free body diagram. And you can see that this is clearly going to be unbalanced, right? We have a much bigger FB upwards than we have an FG downwards, which explains why when you let go of the balloon, it starts accelerating upwards. Unbalanced forces. So your equation is going to look a little bit different in this case. I've got my positive FB up, my negative FG down, but instead of being equal to 0, they're going to be equal to the mass of the balloon times whatever acceleration it experiences as it rises. So this is Newton's second law, F equals ma, or A equals sigma F over m, for the scenario of the released balloon. Okay, a couple quick notes about this, or common misconceptions that it's good to address up front. The first is that the buoyant force does not depend on the depth under the fluid. In the hydrostatic pressure, it definitely depends on depth, but buoyant force doesn't, because buoyant force is the difference in pressure between the top and the bottom, and the difference in pressure doesn't change as the object moves up and down. I think if most people that didn't really understand buoyant force saw this picture to the right, they would say that A and C have different amounts of buoyant force because they're at different places in the water. But the truth is, if they have the same volume, it doesn't matter how deep they are, the buoyant force is the same on either one. Second common misconception is that if the volume of the object changes, the buoyant force changes as well. And in fact, the more volume, the more buoyant force. I think most people would see this and think B has the most buoyant force because it's floating, but actually B has the least buoyant force of these because it's got the least amount of volume under the fluid. So A and C have more and B actually has less. Now B is floating, so there must be something going on with that, but probably what's happening is that the gravitational force on B is smaller than A and C, which is the reason why it's floating. So it has nothing to do with the buoyancy, but it has to do with the amount of mass in the object, the amount of gravity pulling downwards on it. There's also something known as Archimedes' principle, and we'll probably derive this in class, but it's a shortcut. It's a convenient shortcut for many of these problems, which basically says that the weight of the fluid displaced equals the buoyant force on the object. So if I take this heavy weight and I hold it on a scale and it says 5 kilograms, and then I put it into the water, you'll see that 2 kilograms of water would come out of the top of that container. And that means basically that the buoyant force on that block of metal is going to be 2 kilograms. When you read the reading on the scale, it's going to be 2 kilograms less than it was before, because water is going to be holding it up to the tune of basically the mass of 2 kilograms. If you have a floating object, this works as well. So if you have a completely full bathtub and you jump into it and you are floating on the bathtub, the mass of water that comes out is going to be actually equal to your weight, because buoyancy and your gravity are balanced in that scenario as well. So the buoyant force of the water is equal to the mass of water that is being squished out of the tub. Okay, so we're going to take some time now to revisit our essential question, which is, why do things float? And I think the more complete answer that I would give is that things float if the fluid they are displacing provides an upward buoyant force that is equal to or greater than the downward pull of gravity on the object. That's decidedly not a middle school answer, but let's see if we can get back to our middle school answer. Basically, if buoyant force is more than gravity, we're going to be floating. If we plug in some equations for those variables, we know that buoyant force is the density of the fluid times gravitational force field times the volume of fluid that's being displaced. That has to be greater than, now, the equation for Fg, which is the mass of the object times gravitational force field. I'm going to substitute in for the mass of the object, the density of the object times its volume, which is essentially that very first density equation that we came up with earlier in this unit. So we have a new equation that's density of fluid times G times V has to be greater than the density of the object times V times G. At this point, hopefully you're already one step ahead of me. You can cancel out the GV on both sides, and you end up with this. Objects are going to float if the density of the fluid is greater than the density of the object. So now we have a new high school answer, which is that objects float if they're less dense than the fluid they sit in, which is the same as the earlier answer, but now you know why, and you can show it both conceptually, hopefully, and also mathematically through this derivation. I didn't want to leave you without one final comic, which I find pretty entertaining. Again, Calvin takes on floating objects, so hope you enjoy. Thanks for watching.